role, I, Rakesh Jain, working as an assistant professor in Electronics and Communication branch at Geetanjali Institute of Technical Studies, Dabok, Udaipur, want to present you my new lecture video for the topic Operational Amplifier, that is abbreviated as OPAMP. And here we will discuss about the most common type of operational amplifier IC 741. An operational amplifier or op-amp is a high-gain differential amplifier designed as an integrated circuit, that is IC, to perform mathematical operations like addition, subtraction, differentiation, integration, amplification, etc., as well as capable to amplify DC and AC signal. In 741 IC, it is a standard 8-pin general purpose op-amp. Other common ICs are LM324 and LM358, etc. First of all, the pin diagram of IC741. It contains 8 pins. The first of this 741 operational amplifier. The first pin is known as offset null pin. Second pin is inverting input pin. Third pin is non-inverting input pin. Fourth pin is minus VEE or minus VCC, negative supply voltage pin. Fifth number pin is again offset null pin. Sixth number is the output pin. Seventh pin is plus VCC pin, that is plus positive supply pin. At 8 number pin is not connected, it is of no use. The basic symbol for the operational amplifier is it will it is shown like a 741 triangle shape in which this terminal is positive terminal, it is non-inverting input pin, that is third number pin. This pin is negative pin, that is 2 number inverting input pin. 7 number pin which should be connected with the positive supply voltage from 12 to 15 volt is generally used here, plus VCC pin. This pin is fourth number pin, that is minus VCC pin. And this one is sixth number pin, that is my output pin. Operational amplifier parameters. The first parameter is output offset voltage. Output offset voltage is the small unwanted DC voltage that appears at the output of an operational amplifier even when no input signal is applied. Ideally, when both the input terminals of an operational amplifier are connected to ground, that is 0 volt, the output should also be exactly 0. However, due to internal imperfections of the operational amplifier, a small voltage still appears at the output. This unwanted voltage is called the output offset voltage. In simple words, even without any input, the operational amplifier gives a small output, that is output offset voltage. Why does it occurs? Because of the mismatch in internal transistor, small internal bias currents, and manufacturing imperfections. So in a nutshell, we can say output offset voltage is that voltage when we will not provide any input to the operational amplifier, still due to mismatch in internal transistors, small internal bias currents, manufacturing imperfections, there is some output voltage present there. That output voltage without any input is known as output offset voltage. Second is input offset voltage. As we know, output offset voltage is that voltage which is present at the output terminal of operational amplifier without input. So we want to nullify that voltage. With the help of input offset voltage, we can nullify that output offset voltage. To nullify the output offset voltage, we provide a small DC bias voltage between input terminals, that is input offset voltage. Third one is open loop voltage gain. Open loop voltage gain is the gain of an operational amplifier when no feedback is applied. It shows how much the operational amplifier amplifies the difference between its two input terminals. Input impedance. Input impedance is the resistance offered by the operational amplifier at its input terminals High input impedance ensures that the operational amplifier does not draw much current from the input source. Output impedance. Output impedance is the resistance seen at the output terminal of the operational amplifier. Low output impedance helps in driving the load effectively and efficiently. Bandwidth. Bandwidth is the range of frequencies over which the operational amplifier works properly with constant gain. Slew rate. Slew rate is the maximum rate at which the output voltage of an operational amplifier can change. Slew rate can be defined as a rate of change of output voltage with respect to time. Slew rate formula is slew rate equal to dV0, that is change in the output voltage, divided by dt, that is with respect to time. So how much the output voltage changes with respect to time, that is known as slew rate. Unit of the slew rate is volt per microsecond. Slew rate limits the maximum operating frequency for a signal amplitude Vm to present distortion. So the relationship between the maximum operating frequency and the slew rate is given by Fmax is equal to slew rate divided by 2 pi multiplied by signal amplitude Vm. CMRR, that is known as common mode rejection ratio. CMRR indicate how well an operational amplifier rejects common signals present at both input terminals. High CMRR means better noise rejection. It can be defined as the ratio of the differential mode gain AD to the common mode gain that can be shown by ACM. So the formula for the CMRR is the ratio of differential mode gain to the common mode gain. Unit of CMRR is decibels. That is, when we will use 20 log, then it will be converted into decibel. Power supply rejection ratio. Power supply rejection ratio shows the ability of an operational amplifier to reject variations in power supply voltage. This power supply rejection ratio, also known as voltage supply rejection ratio. It can be defined as the ratio of change in input offset voltage to the change in supply voltage. So power supply rejection ratio is given as change in input offset voltage with respect to change in supply voltage. Input bias current. Input bias current is the smaller current required by the operational amplifier at its input terminals for proper operation. It is the average of the two input terminals currents of operational amplifier. See, this is the symbol of operational amplifier in which we have two terminal, inverting input terminal and non-inverting terminal. So there are two currents, inverting current and non-inverting current. As shown in here, there are two currents. So the ratio of these, so the average of these two currents are known as input bias current. Input offset current. The input offset current is defined as difference of the input bias current. So input offset current is the difference, algebraic difference between the I1 and I2, the two input currents of the operational amplifier. Now what is the offset null technique? As we know that without any input there is some presence of output in operational amplifier, that is output offset voltage. One method to nullify that output offset voltage is input offset voltage, means if we provide a small DC bias voltage at the input terminal of the operational amplifier, then also the output offset voltage nullify. One other way is offset null technique. Without any input, the operational amplifier gives a small output, that is output offset voltage. One way to nullify this output offset voltage is by small DC bias voltage between the input, that is input offset voltage. Using offset null technique, we can also nullify this output offset voltage. Offset null technique involve connecting a potentiometer, usually 10 kilo ohm, in between offset null pins, that is 1 and 5th number pin of operational amplifier 741. Middle pin of port, that is wiper, is connected to pin number 4 so as to nullify output offset voltage. See, this one is the symbol of operational amplifier. So if we connect a 10 kilo ohm potentiometer in which in between the offset null pin, that is fifth number pin, and one number pin, and the wiper of that potentiometer is connected with the negative supply pin, fourth number pin, then automatically the output offset voltage becomes nullified. What is the before we will see the different application of the operational amplifier? First thing is virtual ground in operational amplifier. A virtual ground is a node in an operational amplifier circuit that is not physically grounded but is maintained at ground potential due to negative feedback. An operational amplifier follows this fundamental principle that when negative feedback is applied, the operational amplifier drives its output in such a way that the voltage at the inverting and the non-inverting inputs becomes almost equal. If the non-inverting, that is positive 3 number pin terminal is connected to ground 0 volt and negative feedback is present, then the operational amplifier automatically adjusts its output so that the inverting terminal also stays at nearly 0 volt. This inverting input node is called a virtual ground. Input current of an operational amplifier assumed to be 0 during derivations. Why? Because an ideal operational amplifier has infinite input impedance. From basic circuit theory, we know I is equal to V by R. If I want to put R tends to infinite, that is input impedance is infinite, then I must put I equal to 0. So from these two concepts, we will use there in during the time of derivation, that virtual ground concept, and the second one is input impedance is infinite so that the input current is 0. Now what is the difference between the ideal versus practical operational amplifier? So here I draw a chart which show you the difference between ideal op amp and practical op amp in terms of different parameters, or we can say characteristics. The first, input impedance. In case of ideal op amp, the input impedance is infinite, but in practical op amp, it is approximately equal to 2 mega ohm. That is very high. Output impedance. In case of ideal op amp, it is 0, but in practical operational amplifier, it is approximately equal to 75 ohm. Voltage gain. In case of ideal op amp, it is infinite, but in case of practical op amp, it is approximately equal to 2 multiplied by 10 raised to the power 5. That is very high voltage gain. CMRR, that is common mode rejection ratio, which is infinite in case of ideal op amp, but in practical op amp, it is approximately equal to 90 dB. Slew rate. For ideal op amp, it is equal to infinite, but in practical op amp, approximately 0.5 volt per microsecond. Power supply rejection ratio, that is also known as voltage supply rejection ratio, is 0 in case of ideal op amp, but in practical op amp, it is approximately equal to 150 microvolt per volt. Input bias current. Input bias current is 0 in case of ideal, but in case of practical, it is approximately equal to 50 nanoampere. Input offset current. Input offset current is 0 in ideal op amp, but in practical, it is approximately equal to 6 nanoampere. Input offset voltage. Ideally, it is 0, but practically, it is approximately equal to 2 millivolt. Bandwidth. Ideally, the bandwidth is infinite, but practically it is equal to 1 megahertz. Now the block diagram of the operational amplifier. The internal block diagram of the operational amplifier contains 4 steps. First is input stage. There are two inputs. One is non-inverting and one is, as we know, inverting input of operational amplifier, and it will generate two outputs. This input stage is actually dual input balanced output differential amplifier stage. The second stage is intermediate stage, which is dual input unbalanced output differential amplifier stage. Third stage is level shifting stage, which is emitter follower. As we know that common collector work as emitter follower, so emitter follower using constant current source. And the last stage is output stage, from which is known as complementary symmetry push-pull amplifier stage actually, and it will generate the output. Now, first of all, we will derive an application of the operational amplifier as inverting amplifier. Inverting amplifier means whatever the input we will provide at the inverting input pin, it will generate the signal at the output which is opposite in phase with the input. Means 180-degree phase shift we will find out there. So this one is, first of all, we should draw the symbol of the operational amplifier. So this 7 number pin is connected to VCC, means plus 12 to plus 15 volt. Fourth number pin of 741 IC is connected to minus VE. In between 2 and 6, means inverting input pin and 6 number output pin, we connect a resistor which is known as feedback resistor RF. At 2 number pin, inverting input pin, we connect a series resistance, that is R1, where I apply the input signal V input. And third number pin is connected to ground. Now this circuitry is known as inverting amplifier because it contains input connected to the second number inverting input pin and the output is in amplifier form. Now let the inverting input pin voltage V plus, because it is connected to ground, so it is equal to 0. That's why the non-inverting input pin is connected to ground, that is 0 volt. So that due to virtual ground concept, inverting input pin voltage V minus is also equal to 0. Let the output voltage is denoted by V node. Now, the current which is passes through this series resistance R1 is let I1. Now at this node, it will be divided into two parts, one coming towards the inverting input pin and one coming towards the feedback resistor. Let the feedback resistor current is IF and the inverting input current is I minus. I minus is 0, as we already been discussed, that the input terminal pin is assumed to be 0 due to high input impedance. Now, see at node X. From the Kirchhoff current law, we know that incoming current are equal to sum of the all the outgoing current. That's why I1, that is my incoming current towards that node X, is equal to I minus plus IF. Now I1 is what? A current which is passes through the resistor. So from the Ohm's law, I is equal to V divided by R, where V means that voltage difference between the two terminal of the resistor. One terminal is connected to input V in and one terminal is connected to V minus. That's why I1 is V input minus V minus divided by R1. That is equal to I minus. I minus is my 0 here. So I put 0 over here plus IF is what? Current passing through a resistor. One terminal is connected to V minus and one terminal is connected to V node. So the difference between these two voltages divided by RF. So here I am going to write down V minus minus V node divided by RF. Now, as I know, V minus is equal to 0 due to virtual ground concept. So I put in this equation. So it becomes V input minus 0 divided by R1, that is equal to 0 plus 0 minus V node divided by RF. So V input upon R1 is equal to minus V node upon RF. From this, I find out that output voltage equal to minus of RF divided by R1 multiplied by V input. That stands for output voltage is equal to amplifier form of input voltage. And how much it is amplifier? The gain is Rf by R1 and the negative signs show that it is inverting in nature. It means output signal is out of phase compared with the input. Means if the input is sinusoidal waveforms, then output will be just opposite side, start from the opposite side, but in amplify, and the ratio of the amplification depends on what is the gain, that is Rf by R1. So this is my, if I provide a sinusoidal input at input here, then I will find out the output which is in amplifier form, but with opposite 180-degree phase shift is there. So this one is my final formula for the inverting amplifier. Now operational amplifier as non-inverting amplifier. The input signal in case of non-inverting amplifier is applied to the non-inverting input terminal, that is pin number 3, the output signal is in phase with the input signal. Means if input increases, the output also increases. That is non-inverting concept. So again I use the 741 IC symbol first of all. 7 number pin is connected to VCC, that is plus 12 to plus 15 volt I generally use. Fourth number pin is connected to negative supply pin. Second number pin is connected to series register R1, and in between 2 number pin and 6 number pin I connected a feedback resistor RF in between 2 number and 6 number pin. R1, one terminal is connected to ground because I do not want to apply the input at the inverting pin because this is non-inverting amplifier. Third number pin, at the third number pin I apply the input. So here the input is V input. Output voltage is V0, the input voltage is V in, that's why V plus is equal to V in, that is non-inverting pin input. That's why due to virtual ground concept, the inverting pin input is also V input, so as to maintain the gain very high, approximately equal to infinite, and the output voltage is V0. Now RF and R1 form a simple potential divider. See, this one is a resistor R1 which is connected here because no current is drawn at the inverting pin. So this R1 is in series with the RF, where the other point of the RF is connected to V0. So with the help of potential divider network, see here, this one is my potential divider network. Now what is the value of this V input? That is voltage across R1. So from the potential divider rule, I can say V input is equal to R1 divided by R1 plus RF multiply by V node. So from this, V node is equal to R1 plus RF divided by R1 multiply by V input. Now I can simplify it. So V node equal to 1 plus RF upon R1 multiply by input. So output is equal to input multiply by the gain factor 1 plus RF upon R1. So amplify form we find out with positive sign. So it is in phase. The output is in phase with the input. So if the input is a sinusoidal form, then output is definitely amplified form, but with the same phase. This one is my final formula for the operational amplifier as non-inverting amplifier. Now operational amplifier as a summing amplifier, that is known as adder. A summing amplifier using operational amplifier is a circuit that can combine or add multiple input voltages and generate a single output voltage. This one is the symbol of operational amplifier. Again, I will connect the same 7 number pin with plus 12 to plus 15 volt. Minus pin is from minus 12 to minus 15 volt. Feedback resistor in between 2 number and 6 number pin. A series resistance at our inverting input pin. A series resistance R2 at inverting input pin, because here I use inverting configuration. One more resistor, let's suppose I have 3 voltages at the input side. All the resistances are connected to the inverting input pin and I apply the voltages, input voltages here in R1, R2, R3. 3 number pin, that is non-inverting pin, is connected to ground. Now let the voltage apply at one terminal of R1, and in between one terminal of R1 and ground is V1. Second one in between R2 and ground is V2, and the third voltage is in between R3 and ground, that is V3 voltage. Let the output voltage is denoted by V node. So here we use the simple principle by considering one voltage source at a time, and the rest one is connected to ground. So only one voltage is applied, but these voltages apply at the inverting input pin. That's why it behave like a inverting amplifier whose gain is given by minus feedback resistance divided by the series resistance multiplied by given voltages, as we already been discussed the inverting amplifier. In this setup, the input signal are connected through resistors to the inverting input of the operational amplifier. Step number 1, when only V1 is present. So what is the first output voltage? Let it is V node 1. So V node 1 is minus RF upon R1 multiplied by V1. Step number 2, when only V2 is present. So the output voltage is equal to minus Rf by R2 multiplied by V2. Step number 3, when only V3 is present, then output third, that is V naught third, is equal to minus Rf by R3 multiplied by V3. So if R1 equal to R2 equal to R3 is equal to Rf, we put all the resistance equal to each other, that is equal to a single value R. See in the diagram, all the resistances are now equal to R. Then these three voltages becomes, this first voltage is equal to minus V1 because Rf to R1 cancel out because both are of similar value R. Similarly in second case and in third case, so the second voltage is minus V2 and third voltage is minus V3. So the final output voltage is the sum of all these three voltages. So that is equal to minus V1 plus minus V2 plus minus V3. Minus is common in all these three terms. So it is the output voltage is equal to the sum of all the three voltages, and if this negative sign show that all the voltages are applied at the inverting input pin. This one is my final formula for the operational amplifier as summing amplifier or adder. Now operational amplifier as a average amplifier. Here also we will use the same inverting configuration. An averaging amplifier using an operational amplifier, that is op-amp, can be designed to produce an output voltage that is the average of multiple input voltages. This one is the symbol of operational amplifier. Here I will do the same connection. 7 number pin with plus 12 to plus 15. Fourth number pin connected to the negative supply. Feedback resistor in between 2 and 6 number pin. Series resistances are connected. Let R1, R2 and R3. One side is connected to the second number pin and one side is connected to the different input potentials. Third number pin is connected to ground. All the potentials are respectively V1, V2 and V3 in between the resistance 1 lead and ground, and let the output voltage is V node. Here we do not put R1 equal to R2 equal to R3 is equal to Rf. Instead of that, what we are going to do, in this setup, the input signals are connected through resistors to the inverting input of the operational amplifier. The same step when only V1 is present, so the output is equal to minus Rf by R1 multiplied by V1. Step number second, when only V2 is present, then output second is equal to minus Rf by R2 multiplied by V2. Step number third, when only V3 is present, then output third is equal to minus Rf by R3 multiplied by V3. So if I put R1 equal to R3 equal R2 is equal to R3 is equal to R. See, in the last case of adder, I put R1 equal to R2 equal to R3 and also the feedback resistor is also equal to R. But here only the series resistances are equal. See in the diagram. And if feedback resistor is equal to R by N, where the meaning of N is number of input, because here V1, V2, V3, 3 input. So I put 3 here. So see in the diagram, R1 equal to R2 equal to R3 are same value resistances, but Rf equal to R by 3, one third of these series resistance. Then the first output voltage becomes minus V1 by 3, second output voltage becomes minus V2 by 3, and the third output voltage becomes minus V3 by 3. So the final output is the sum of all these three voltages. So it becomes sum of these three voltages, and if I put minus as common, then it is equal to sum average of these three input voltages V1 plus V2 plus V3 by 3, and this negative sign show that we use the inverting configuration because the input are applied at the inverting input pin. So this one is my final formula for the operational amplifier as average amplifier. Now operational amplifier is a scalar or scaling or weighted amplifier. If each input voltage is amplified by a different factor, that is weighted differently at the output, the circuit becomes a scaling or weighted amplifier. See the symbol of the operational amplifier, the same type of connections we are going to do. 7 number is connected with the positive supply, 4 number with the negative supply, feedback resistor between 2 number pin and 6 number pin. Series resistor is resistances are connected at 2 number pin, third number pin is connected to ground. Voltages are applied respectively V1, V2 and V3 in between the resistor 1 lead and ground. 6 number pin is the output voltage. In this setup, the input resistors are connected through resistors to the inverting input of the operational amplifier, but with a minor change that instead of put equal these resistances like in adder, or series resistances are equal and Rf equal to R by N. Here we are going to use the concept that all the resistances are of different value. So step number 1, when only V1 is present, so the output 1 is equal to minus Rf by R1 multiplied by V1. When only V2 is present, then output is equal to minus Rf by R2 multiplied by V2. When only V3 is present, then output third is equal to minus Rf by R3 multiplied by V3. So the output voltage is the sum of all these three voltages. So I put the values from there. So this becomes first output plus second output plus third output as we find here. Now this one is known as scalar. Negative sign show because inverting terminal is used to apply the voltages. So this one is my final formula for operational amplifier as a scalar or weighted amplifier. Now operational amplifier as a subtractor. Operational amplifier as a subtractor is a circuit that produces an output which is equal to the difference of the inputs. So similar kind of connections I am going to do for the basic symbol of the operational amplifier. 7 number pin is connected to positive supply, 6 number with the negative supply. Feedback resistor between 2 number pin and 6 number pin. Series resistor is connected, a single series resistor R1 is connected at pin number 2. Let the voltage at this second terminal of the R1 is V2 voltage. The third number pin is connected to R2 resistance and the supply voltage is V1. Let one lead which is connected to the third number pin is connected to be connected via a resistor to the ground. Let the resistor is R3 and let the output voltage is V node. So see, step number 1, when only V1 is present. When I consider only V1 is present, so V1 is applied at the non-inverting input pin. So the output becomes follow the rule of non-inverting input. And what is the non-inverting in formula? Output is equal to 1 plus Rf divided by R1 multiplied by the voltage which is present at the third number node. Here the voltage is whatever the voltage across this R3 resistor. So this circuit looks like this one. I consider V2 is not present, only V1 is present. Let the voltage at the inverting input pin is denoted by V plus. So this is the voltage which is across the R3 resistance. So V plus is equal to, from the basic potential divider rule, R3 upon R2 plus R3 multiplied by V1. So V node 1 is, what is the output voltage in the first step? That is equal to 1 plus Rf upon R1 multiplied by whatever the voltage present at the non-inverting input pin, that is V plus. So this becomes, here I put this V plus value here. So V node 1 is equal to 1 plus Rf by R1 multiplied by R3 divided by R2 plus R3 multiplied by V1. That is equation number 1. Now in the equation number second, here I find this equation. This one is step number 1. Now for the step number second, when only V2 is present, the circuit looks like this one. Only V2 is present, which is connected at the inverting input pin, and the third number pin is connected to the ground. Then it becomes an inverting amplifier. So output second is equal to, from the inverting concept, minus Rf by R1 multiplied by V2 voltage. This is equation number second. Now, if I put all the resistances are equal to each other, then see these two equations. These equations become, if all the resistance are equal to each other, so cancel out, only V1 will be present. So the output first becomes V1. And here in the second equations, when resistances are equal, then only minus V2 will be present. So what is the final output? That is the sum of all these two step output. So it becomes V0 equal to dif difference of these two inputs. So it is known as subtractor. So this one is my final formula for op-amp as a subtractor. Now operational amplifier as a differential amplifier. It means a amplifier which can present the difference but in amplified form. So output is equal to difference of the input with amplification. Now see the same circuitry here I use 7 number with plus VCC, 4 number with minus VE. The same subtractor circuit I am going to draw. RF is connected between second number pin and 6th number pin. Series resistance R1 is connected and the supply voltage is V2. Let third number pin is connected to the R2 resistance. Supply voltage is V1. One terminal of third number is connected to ground via a resistor R3 and let the output voltage is V0. So this one is the same diagram which I drawn earlier in the case of subtractor, but with a minor change we can use it as a differential amplifier. Now when only V1 is present, we saw in the subtractor that output is equal to equation number 1, which is here, and when only V2 is present, it becomes a minus RF by R1 multiplied by V2. What I am going to do here in equation 1, put R1 equal to R2 and R3 is equal to RF. If in the circuit of a subtractor, if I put this R1 equal to R2 and RF equal to R3, then it becomes a differential amplifier. How it possible? See the both of these two equations. So in the first equation, if I put R1 equal to R2 and R3 is equal to RF, it becomes plus R1 divided by R1 multiplied by V1. And similarly, the what is the output voltage second? Minus RF by R1 multiplied by V2. This one is now equation number third. So output is the sum of both of these equations of V node equal to V01, that is here equation number third, plus V node 2, that is equation number 2. So the final output is equal to difference of these two input but multiply with a gain factor RF by R1. So this one is the final equations for the operational amplifier as a differential amplifier. Now operational amplifier is a voltage follower. A voltage follower, also known as unity gain buffer, using operational amplifier is a circuit where the output voltage follows the input voltage, means output equal to input. That is gain equal to the ratio of the output upon input. If both are equal, then the gain is 1. So this one is the operational amplifier. 7 number pin is connected to plus supply voltage, 4th number with negative supply voltage. Here I apply the input at the non-inverting pin, which is V input, and 2 number pin is directly connected to the 6 number pin, which is V0 pin. So 2 number is connected to V0. So this circuit becomes operational amplifier as a voltage follower. Why? Because we know that output is directly connected to the second number pin. So the voltage at the second number pin, inverting pin, we consider as V minus. So output is equal to V minus. Because V plus terminal, that is non-inverting input voltage terminal, is connected to input supply. That's why V plus equal to V input. Due to virtual ground concept, this V minus is also equal to whatever the voltage present at the non-inverting pin, that is V input. So V minus equal to V input to maintain the gain very high. So now if I put here, then output equal to input. So this one is the final equation which show that in voltage follower the gain is unity. So it is also known as unity gain buffer. So gain is output upon input, that is equal to 1. If I provide a sinusoidal voltage at the input side, I will find out the same kind of sinusoidal voltage at the output side. Now very important application, that is operational amplifier as a differentiator. Operational amplifier is a differentiator circuit produces an output voltage signal which is time derivative of the input signal. That is output voltage is equal to the differentiation of input voltages. See the operational amplifier circuitry for the differentiator. 7 number pin is connected to plus VCC. 4 number pin is connected to negative supply pin. Here a register, feedback register is used as it is, but In the operational amplifier differentiator circuit, the input register, that is series register, has been replaced with a capacitor. So let a capacitor C1 is connected here in between two number pin and input, that is my V input. Third number pin, that is non-inverting pin, is connected to ground. Let the output non-inverting pin voltage is equal to 0 due to virtual ground concept. This inverting input voltage is also equal to 0. Now the current will flow through this V input is, let's suppose, I1 via the capacitor. Now at this node it will be divided into two sections. One side via feedback register, that is denoted by IF. One side at the inverting input pin, that is denoted by I minus. Due to maintain the input impedance very high, we consider approximately equal to 0. Let the output voltage is V node. So at this node, see the Kirchhoff current law, incoming current equal to the sum of outgoing current, that is I1 equal to I minus plus IF. What is the I1? When a current passes through the capacitor, the current is given as C d by dt of voltage difference between the two terminal of the capacitor. So here one terminal is connected to V input and one terminal of the capacitor is connected to V minus. So C1 d by dt of V input minus V minus, that is equal to 0. To maintain the high input impedance approximately equal to infinite, we consider current equal to 0 plus current passing through the feedback register. So current passing through the feedback register is voltage difference in between two terminal of resistor. One terminal is connected to V minus and one terminal is connected to V node. So V minus minus V node divided by RF. Due to virtual ground concept, V minus equal to 0. So when I put in this equation, it becomes C1 d by dt of V input minus 0. That is equal to 0 plus 0 minus V node upon RF. So what is V node from this? V node is equal to minus RF C1 d by dt of V input. So from this equation, we can see that output is equal to derivative of the input. That's why it is known as differentiator. This one is my final equation. Now due to this, see the different waveforms. If the input is sine, then output will be cosine. See, when I apply the sine wave at the input side, the output will consider a cosine waveform. If the input is squared, then output will be spikes. So when I consider this square wave shape at the input side, I will find out that output contains this spike shape. If I provide a triangular at the input, then output will be rectangular. See this, if I provide a triangular wave shape at the input, I will find out the output which is squared shape. So this one is operational amplifier as a differentiator. Now operational amplifier as a improved operational amplifier, differentiator amplifier. Due to instability and noise, the basic single resistor and single capacitor operational amplifier differentiator circuit is not basically used. To reduce the overall closed loop gain of the circuit at high frequencies, a series resistor R1 is added to the input. And to further suppress the higher frequency signals, a capacitor CF is connected in parallel with the feedback resistor RF in the differentiator circuit as shown below. So this one is the practical differentiator circuit. Here we have to do one minor change. One parallel capacitor is added in the feedback path and one series resistor is added in the inverting side. Now operational amplifier as a integrator. As the name implies, operational amplifier as integrator circuit produces an output voltage signal which is equal to the integration of the input signal. It uses a feedback capacitor CF instead of a resistor to produce an output voltage V node which is proportional to the negative integral of the input voltage. See the circuitry. First 7 number pin is connected to positive supply. Negative pin is as it is minus voltage. In between 2 and 6 we consider here a capacitor instead of a resistor, that is CF. So feedback capacitor CF is connected between 2 number pin and 6 number pin. A series resistor is added at the inverting input pin, let it is R1, and the input signal which is applied at one terminal of this R1 is V input. Third number pin is connected to the ground potential. So the node voltage at the third number pin, that is non-inverting terminal voltage, is 0 due to virtual ground. This inverting terminal voltage is also 0. Let the output voltage is denoted by V node. Let the current passing through this R1 resistor is I1. It will be divided into two sections. One is the feedback current and one is the inverting current. Inverting current is I minus, that is equal to 0 to maintain the high input impedance approximately equal to infinite. So current is 0. One current is in the feedback path, that is IF. So from the Kirchhoff current law we can say I1 is equal to sum of I minus plus IF. I1 is the current which is passing through a resistor, which is given as V input minus V minus divided by R1, that is equal to 0 to maintain the high input impedance, I minus equal to 0. And IF is the current through a capacitor, which is given by CF d by dt of V minus minus V node. And we know the inverting input potential to maintain the virtual ground concept is equal to 0, as non-inverting is also 0. So put this value in this equation. So V input minus 0 divided by R1, that is equal to CF d by dt of 0 minus V0. So it becomes V input upon R1, that is equal to minus of CF d by dt of V node. From this, we will find out the final expression of V node. V node is equal to minus 1 upon R1 CF. And when differentiation will move at this side, then it becomes integration of input. So from this, we can consider output is the integral of the input. This is my final expression. Now see the different waveform. If I provide a sine input, it will generate a cosine output. So see, if I provide a sine input, it will automatically generate a cosine output. Now, if I provide a square input, then it will generate a triangular output. So if I provide a square wave at the input side, it will generate a triangular shape at the output side. And if I provide a triangular input, then parabolic output I will find out. So if I provide a triangular input, see the waveform, the output becomes a parabolic shape. Now, in an operational amplifier integrator, the feedback capacitor alone gives ideal integration, but practically it creates serious problems. A feedback resistor is connected in parallel with the capacitor in operational amplifier integrators application to limit the DC gain, prevent the output saturation due to offset voltages, improves the stability and ensure proper low frequency operation, thereby making the integrator practical as shown in the figure. So see the practical integrator circuit. Here I do one minor change, a resistor which is connected in the feedback path, that is RF, which is parallel to the CF. This one is practical integrator.